Oh look, more death by PowerPoint. This time we're looking at floating point numbers. This is how we render fractional numbers in binary. This is of course part of 9.4.2, the interrelationship between hardware and software, as part of the software design and development syllabus. Let's get started. What is a float? Well, the IEEE, that's the Institute of Electrical and Electronics Engineers, the IEEE, Standard 754 defines how computers render real, that is to say fractional, numbers. We will learn about a single precision floating point operator, and it's got a very specific structure. It's always the same. It's always 32 bits long. The first data bit is always a sign bit. Again, 0 for positive, 1 for negative. There is always an 8-bit exponent, which we'll deal with soon, and a 23-bit mantissa. Now, two new terms there, exponent and mantissa. We will learn about those as we go through this presentation. To do this, we're going to look in detail at how it's done. We're going to convert the number 87.125 to be a floating point number. And it is easy to do, albeit complex, albeit not complex, in depth. So for starters, we'll do the easy bit. A sign bit, you've already met this, sine and modulus. Remember a couple of presentations ago we looked at different ways of rendering negative numbers. Well, 0 for positive, 1 for negative. Simple. The exponent. This is where it gets a bit tougher. The exponent is how far you shift the binary point plus 127. And we'll see how this works. Think about scientific notation. It's going to help a lot, actually. We can express really big numbers really easily. Now, this is Avogadro's number. Avogadro's number calculates the number of atoms in that many grams of a substance or whatever. Anyway, it's a known number in science, 6023 with lots of zeros, or if you like, 602 sextillion. Numbers that are just stupidly big. We don't render all those zeros. We use scientific notation. So we understand this number as being 6.023 times 10 to the 23rd power. The 23 part here is the exponent. There's 23 zeros or 23 values after the decimal point. So if I created a floating point number with decimal points, which I don't, but it's a good thought experiment, my exponent would be 127 plus 23 because I shift the exponent 23. I shift the decimal point 23 values. So my exponent will be 127 plus 23 is 150. So that's the concept. Remember, I've got this massively huge number with lots of zeros after the decimal point. So I use an exponent. That exponent there is the exponent I'm going to deal with when I start looking at it in binary. Let's see how this works with binary numbers. So, first and foremost, when you have a decimal number that is between 1 and 0, you have a number with a decimal point. In binary, it's called a binary point. So a fractional number, such as 2 3/4, can be written as 2.75 and it's easily understood. We know the number to the left of the decimal point represents a whole number. We know the values to the right of the decimal point represents the fractional part between 0 and 1, or 0 and minus 1. The same can be said on a binary number line. It stretches both sides of the binary point. So we can convert 2 3/4 to binary really easily. We start with our number line, but this time it's a bit different. You'll see we have the whole number values on the left-hand side and the fractional values on the right-hand side. So 0.100 is a half. 0.010 is a quarter, or 0.25. 0.125, or 1/8, or 0.001. Okay, so when we're doing our conversion, 2 is 0.10. Now, to get to 3/4, it's a half plus a quarter. If you like, 2 quarters plus 1/4 equals 3/4. 2 quarters plus 1/4 equals 3/4. So therefore the answer is 10.11. That's how I get 2 3/4 into binary. Now please, if you need to rewind the video and re-watch that, or write it out a couple of times, please do. That's the hard part of working out an exponent. So remembering back to Avogadro's constant with all those zeros and scientific notation, the exponent was 23 because the number was 6 times 10 to the 23rd power. Let's do this with binary numbers. Let's convert 87.125 to binary. So 87 is 101011, and then the 0.125 is 1/8, so 0.001. So there is my binary number. Now that's going back and reminding myself of what I've done in the past few presentations, the early part of these presentations, about converting binary numbers decimal numbers to binary. I've just extended it by making it a fractional part as well. Here's the fun part. There's my binary point there. When I work out my exponent, it moves. Let's see. I'll do that again. So 87.125 in binary is 101011.001. To read this in scientific notation, I need to remove the binary point to the left. In fact, I move it 6 spaces. 1, 2, 3, 4, 5, 6. So moving that binary point from there to there means I've moved it 6 spaces. So the exponent is 6. And 127 plus 6 is 133. So now if I'm converting 87.125 into a 32-bit binary float, I know 2 parts of the answer. The sign bit, 0, because it's positive, and the exponent, 133. Except the exponent needs to be expressed in binary, obviously, because I'm dealing with binary numbers. So 133 in decimal reads as 1000101 in binary. So I've got the first 2 parts of my floating point number sorted. The sign bit and the exponent. Now the fun part, the mantissa. A mantissa is everything after the binary point totaling 23 digits. So that's my number, 1.0101101. That's my number. Everything after the binary point, 0, 1, 0, etc., is the mantissa. And then because it needs to be 23 bits long, I'm going to add 14 zeros. The mantissa is always 23 bits long. Now notice something. This number, this leading 1, is not rendered. There is a reason for that. So when we put it all together, 87.125, the sign bit is 0, the exponent is 133, which is all that, and the mantissa is everything after the binary point. Now, notice a leading 1 with the arrow pointing to it is not rendered in the mantissa. It is always assumed. This is because it can be assumed. There are only 2 numbers in binary, 0 and 1. Because the first value, once I've worked out my number in binary, the first value before the decimal point or the binary point is a 1. It must be a 1. It can't be a 0. It can be assumed. 0 is never the first value in scientific notation. And because there is only 2 values, 0 and 1, the 1 can be inferred, which actually makes my mantissa 1 step more accurate. It can be, although it's 23 numbers long, it refers 24. That's pretty cool. Okay, there are 6 edge values when dealing with floating point numbers, and these are always brought up in exams. So we have to deal with them. We have positive 0, negative 0, positive infinity, negative infinity, a positive value which is too big, anything other than, a positive value that is not a number, and a negative value that's not a number. Now look at these bottom 2. 0 means positive, 11111 means infinity, and any number in the mantissa that is anything that includes any number of values that aren't 0 is not a number. It's defined as being an error. Positive more than infinity, basically, which is impossible, hence the reason it's declared as not a number. The other value, 1 with lots of 1s, so that's negative, infinity, and any number other than 0 is again minus less than infinity, or less than minus infinity, so that is not a number. These two are declared and defined by the standard as being not numbers. There are 2 0 cases once again. positive 0 and negative 0. And then plus and minus infinity. Thinking time. Can you represent -1 and +1 as floating point numbers? Show your working. Okay, so pause the... I'm going to explain how to do it. Pause the video and try and work it out for yourself. So here's the explanation first. You need to work out the 3 different components: the sign bit, the exponent, and the mantissa. So work out what is 1 in binary, 1. Work out the exponent, 0. So therefore it's actually 127 plus 0 is 127. And the mantissa. Do that for -1 as well. Pause the video, do some calculations, see if you get it right. And if you've tried, let's see how you went. Hopefully you got that right.